Let's last time we are starting about the analysis of a half-wave rectifier. Let's now we'll go for this one half-wave rectifier. We have seen okay. Last time we have come up to this point. Yeah, I am audible. Screen is visible. Please reply. Electrical guys. Please reply. Any one of you.
Yes, sir.
Yeah. Okay. Lastly, we have started the half-wave rectifier. We have seen their working operation associated with the half-wave rectifiers and analysis we have started considering the number of parameters like average voltage and average current, RMS current and RMS voltage, and voltage regulation, ripple factor, important ripple factor, which is a 1.21%, transformer utilization factor, and efficiency of the circuit. So the disadvantage of a half-wave rectifier, it is seen that it has low rectification efficiency, which is a 1.21%. Okay. Next, it's have a low TUF or a low rectification efficiency. So half-wave rectifier is suffering from a excessive ripple, low rectification efficiency, and the transformer utilization factor. And also that here for half-wave rectifier, it is seen that transformer secondary voltage is available for an entire one cycle from 0 to pi and pi to 2 pi. But diode conduct during the positive half cycle since it is acts as a forward bias for a positive half cycle. So therefore current will be flows through a load. So positive half cycle current is flowing through load. Whereas for the negative half cycle of a input transformer secondary input, the diode behave as a reverse bias and no current is flow. So finally we can say that here the current is flowing through the circuit during the positive half cycle, not during the negative half cycle. So therefore, there will be a no cancellation of a secondary current during the entire cycle. Only positive cycle is a current is flowing, negative cycle is a current not flowing. So therefore, there will be a for at a transformer, there is a transformer DC saturation takes place at the transformer secondary winding. Yeah. So next guys, the numerical based on this one from a number of analysis. So you have to try it yourself. For half-wave rectifier, the resistance of a transformer secondary is a 5 ohm. Forward resistance RF is a 50 ohm. Load resistance is a 1 kilo ohm. And the turn ratio is a 4 as 1. Now we want to calculate here average voltage and the average current, RMS voltage and RMS current, rectification efficiency, and the transformer utilization. So basically, we want that for a finding here for VDC, VDC is given as a VM divided by pi. IDC is given as a IM divided by pi. ILRMS is given as a VM divided by root 2. VM divided by 2, and the ILRMS is also given as a IM divided by root 2. And the efficiency is involving the expression in terms of RF and RS and RL. Transformer is also same. So from all these expressions, it is seen that we require VM and IM that. So it's now our job. We need to find VM and IM. So once you have, we will get here the number of parameters we can calculate. Now how to find the VM or IM? So here it is seen that turn ratio is provided you 4 as 1. Yes. So transformer secondary rating is given. Transformer secondary rating is provided in terms of a turn ratio. We know that the turn ratio is having a relation with the voltages on a primary side. So primary voltage is directly proportional to their turn ratio, or secondary voltage is directly proportional to secondary turn. So therefore, we can get the VRRMS, so we can write the secondary voltage of RMS is directly proportional to the secondary turn ratio, and the primary turn voltage, primary RMS voltage is directly proportional to the primary turn ratio. So the examiner has provided this information as a 4 as 1, which is a n as a np as a ns is equal to 4 as 1. So if it rearrange this one, you will have this value will be 1 by 4. So if we get it 1 by 4, yes, it's 1 by 4, then can you find transformer secondary rating? Transformer secondary rating, you will have the ns divided by np into primary voltage of a transformer. Let if we consider primary voltage of a transformer is a calculation point of view a 240. Actually it's a 230. It's a secondary voltage, primary transformer voltage is a generally from 180 to 240. So we will consider that for calculation point of view, assume that the transformer primary voltage is a 240. If we consider this one as 240 here, 240 into turn ratio, which is given as a 4 as 1 primary to secondary. So secondary to primary it is 1 as 1 divided by 4 into the primary. So 1 divided by 4 into 240 gives you the transformer secondary voltage. Yes, so 1 divided by 4 into 240, which is a 60. This 60 value is there, and we have the relation between the transformer secondary voltage and its a transformer peak. So the relation between peak and the RMS is given as a Vm is equal to root times its RMS value. Remember that, guys. The RMS value is the root times. So it's a root 2 value is approximately 1.414. 1.414. Approximately it's a 1.5. So if I say that this value is a 60, approximate value will be a 90 if we consider 1.5 approximate, but actual value is a root 2 value is a 1.414. So if we consider this, you will have 84.8 volt is a Vm. So once you have the Vm, can you find the VDC? So VDC is given as a Vm divided by pi expression. Yes. So VDC is given as a Vm divided by pi. IDC, can you find the IDC? IDC is given as what? Im divided by pi. So now my role is that I want to find out Im. So what is the relation between Im and Vm for a half-wave rectifier? For Im is given as a, yes guys, Vm divided by resistance offered by transformer secondary, resistance offered by resistance offered by diode RF, and the load resistance. So they have given that transformer secondary as a 5 ohm, RF as a 50, and load resistance as a 1. So you will have this is a 1055 is a total resistance offered by that branch. This value is divided by this value should be divided to this V1. So you need to find Im. So once you have Im, you will get the IDC. So this value you have. So IDC you will have 26.6 milliampere and 26.6 volt is a voltage. So guys, you need to find these values. Similarly, what is the ILRMS and the VLRMS? VLRMS is given as Vm divided by 2. ILRMS is given as a Im divided by 2. So you have to find these two values. So the rectification efficiency, what is the rectification efficiency? Rectification efficiency is given as a PDC divided by PAC. And PDC is given as a IDC square into RL. So IDC already you have found out in this expression. And PAC we want to find out. So PAC is given as a IRMS square into RL. So IL RMS you have found out it. So simply plug that, you will have this value as a 38.5%. Now TUF is given as a what? It's a transformer utilization factor is given as a PDC divided by PAC rating. And for that you have to find out all these values. So guys, this is a homework for you. You have to try it at your end. So one more numerical for halfway rectifier. Again, this one, guys, I request all of you, I have provided here three numericals. You have to take a screenshot of these numericals and you have to try it at your end. Now for here we will certainly discuss the solution and you have to find out it. So for halfway rectifier, the transformer secondary voltage is a V is equal to 30 sine omega t and RL is equal to 500 ohm is used. Assume that transformer secondary resistance and the diode resistance is a 30 ohm. So again we want to find out the parameters. The DC voltage, DC current, RMS voltage, RMS current, rectification efficiency and the voltage regulation. So we need to go. So for this we want the VM. And here if we compare this expression, V is equal to 30 sine omega t with a standard equation V is equal to Vm sine omega t. So you will have the here Vm. So here guys, in this problem Vm is provided directly. In the previous problem Vm is given in terms of their turn ratio. The VM in the previous problem, VM is not directly provided. It's provided in terms of a turn ratio. So if you compute here VM, rest of the further things are easy to calculate by knowing their expressions. Okay. So these are the values will be there. Okay. You have to cross check it at your end. Now third problem. Yeah, it's a halfway rectifier consists of a diode forward resistance 1 ohm, transformer whose open circuit secondary voltage is 12 volt. Assume that RS is equal to 3 ohm. Find no load voltage regulation and the DC output voltage for the DC load current of a 100 milliampere and voltage regulation. What is no load voltage regulation for a full wave rectifier? Sorry, half wave rectifier. It is given as a VNL is equal to Vm divided by pi. Vm divided by pi. Can you find the Vm here? Can you find the Vm here? Yes. It's the RF is given you. Transformer secondary voltage is provided. Open circuit voltage provided is given. So you have the Vm is a 12 guys here. So you have the Vm divided by pi, which is a no load voltage. Now second task, DC output voltage for a DC load current of 100 milliampere. So what will be that expression? The expression VDC is equal to Vm divided by pi minus IDC into RS plus RF. So we have the VDC in the number of forms. So out of that we have studied, we will take a expression in terms of which is available in terms of Vm and IDC. So simply we plug the values of this one. Yes. So we have here that IDC is given as a Vm divided by pi into Rs plus Rf plus RL. This is a IDC, sorry, this is the Im values. So Im value you have to find out its, and from that one you have to find out IDC, which is given as a Im divided by pi. Or simply you can plug this Vm divided by pi is nothing but Im, and so you will have this expression. So you have to try it yourself. So you have here is a load voltage, you have the full load voltage at a 100 milliampere we want to find out. So this need. And the finally voltage regulation is given as by basic definition, no load voltage minus full load voltage divided by full load into 100. So already you have found these two parameters in the previous calculation 1 and 2. So simply plug this and you have to find out that. So at the end you will have these are the answers. So guys, I request you have to take a screenshot of this one and you have to try it at from your end with a pen and paper. You have to try it and then solve this problem. So this will be one of the problem will be for the assessment and for, or like this format, the sample format will be provided for the exam assessment. Okay, I hope you have taken a screenshot of this one. So we'll move for the next topic, full wave rectifier. Before starting this full wave rectifier, I request all the students. So you have logged on a WebEx platform. I request all of you, you have to edit your profile as your serial number space surname space first name. I repeat that everyone guys has to edit their profile as a serial number space surname space and the first name. And whenever you are logging to our web lectures, every time make essential that every time you should be a log with this your profile. Every time if you disconnect it, again you have to edit your profile, so that when once we check your attendance on the WebEx platform, whether you are attended or not, we will have the record. Even also we are taking your attendance also on the WhatsApp group also. That so it means that if you are attended the lectures, then you have to submit the attendance on a WhatsApp. If you are not attended, don't send it. If you misbehave, you will be identified through a WebEx platform. So guys, so take it. Now we have seen that half wave rectifier. What are the problems associated with half wave rectifier? First problem is that low rectification efficiency. Second problem is that excessive ripple. Third problem, efficiency is low. And the fourth is DC saturation. Now why DC saturation is there? Because the current is flowing only during the positive half cycle, not for the negative half cycle. So current flowing through transformer secondary is not for the entire cycle. It's only for the positive cycle. So therefore, the transformer secondary DC saturation is a takes place in case of a half wave rectifier. So can we resolve this problem? Yes, we can resolve this problem in spite of using a normal transformer. Can we use a center tap transformer? Yeah. So if we use the center tap transformer to the transformer, so transfer at the transformer, so then we have a circuit arrangement. Yes, it's a like this way. So here we have here a transformer is a center tap transformer. This one is point is a CT point is a center tap. So yeah, assume that here turn ratio of a primary of first half of a primary is the same as with first half of a secondary is the same as with the latter half of a secondary is there approximately guys. So here it is a CT point, or general it is a ground point will be there. So again here the transformer is a step down transformer. So here primary is a converted into the secondary voltage by using a step down transformer. Now let's guys, we'll look at its working operation associated with this diagram. So here this circuit is using a center tap transformer. So it's a center tap circuit, and it's a behave as a full wave rectifier. So it's a called as full wave. How that we will take a discussion on this one. So what will that? So let's, if we consider your input signal is applied to the from a primary, the secondary voltage is available at the transformer secondary, which is a sine wave here, and here it is also sine wave. So what is the relation between these two, upper half of a transformer secondary and lower half of a transformer secondary? The relation between upper half of a transformer secondary and the lower half of a transformer secondary is that both are out of phase. Means there is a phase difference between upper half of a transformer and the lower half of a transformer is a 180 degree. So means if you consider this is a solid line, is a transformer secondary voltage of a upper half. So dotted line is represented as a transformer secondary of a lower half section. Okay, so you will have now where it is one cycle starts from a 0 and end at a 2 pi. So this is a one entire cycle. So for one entire cycle, during the positive half cycle, upper half of a transformer is a positive and the lower half of a transformer is a negative during the positive during the interval 0 to pi. At the same time, for a pi to 2 pi interval, upper half of a transformer is a negative and the lower half of a transformer is a positive from this waveform. Now we will concentrate first half cycle for interval 0 to pi. So during this interval, upper half of a transformer is a positive, lower half of a transformer is a negative. So here you will have the positive voltage at the upper here, and here it is a negative, and here you will have a negative, and here it is you have the positive. So therefore this terminal is a positive with respect to CT or with respect to negative. So this positive terminal is applied to the diode, and this negative terminal is applied to the this cathode terminal through the load resistor. It's a minus. So means this upper terminal is a positive is connected to the anode side, and the negative terminal is connected to the cathode side of a D1 diode. So therefore diode D1 is a forward bias. As it is a forward bias, it will behave as a closed switch. As it is a behave as a closed switch for under ideal condition, then this transformer secondary voltage is applied to the load. So therefore the current will be flows through load is from top to bottom. Through a load is a upper positive to the lower positive during the positive cycle. Okay. What about diode D2? For during the interval 0 to pi, lower half of a transformer secondary is a negative. So this will be a minus and this will be a plus. So this negative is applied to the anode terminal of a D2 and this positive is applied to the cathode terminal of a D2. So therefore this diode D2 will be a reverse bias. So as it is a reverse bias, if we consider diode is ideal, it will be open. So therefore, the voltage is not applied to the load here. So no current will be flows through a diode D2 during the interval 0 to pi. So finally we can say during the interval 0 to pi, D1 is a conductive and D2 is a non-conducting gate. So therefore, the voltage is available at the load due to the conduction of a D1. So it's indicated at D1 on and D2 off. So as the input is available here, so the shape of the output available at the load shape is given as a like this way. So if we consider now this one interval 0 to pi we have considered. Now what about the pi to 2 pi? For a pi to 2 pi, upper half is a negative and lower half is a positive. So definitely this terminal will be positive, this terminal will be negative. Yes. So the positive terminal of a transformer is connected to the anode and negative terminal is connected to the load. Yes. Negative terminal is connected to the load here, sorry, connected to the cathode terminal of a diode D2. So therefore, this diode D2 will be a forward bias. So as it is a forward bias, if we consider ideal diode, then it is a closed switch. This input voltage is applied here like in this way. So you will have the current direction will be from a transformer secondary up lower transformer secondary is like in this manner. So again the current will be flows from a top to down of a RL. So the direction current flowing through for interval 0 to pi is a top to bottom, and for interval pi to 2 pi again a top to bottom. So current is flowing through load in both the half cycle will be the same direction. So finally you will have the voltage will be developed here. So what about the D1? So at the D1, the transformer secondary of a upper half of a transformer secondary is what will be your upper half of a transformer secondary is what? Yes, upper half of a transformer secondary is negative. Yes, upper half of a transfer secondary is negative. So this negative terminal is connected to the anode terminal of a D1 and the positive terminal is connected to the cathode terminal of a D1. So diode D1 is reverse bias. So as it is a reverse bias, this transformer secondary voltage is not applied to the load since for a reverse bias it's a behave as a open switch. So like in this way, for interval 0 to pi, and for a pi to 2 pi interval, current will be flowed through a diode from forming a terminal, upper terminal as a positive and the lower terminal as a negative. Since during the positive half cycle, D1 is a conducting, and during the negative half cycle, that D2 is a conducting, and the rest diode D1 will be remains off for pi to 2 pi, and remains off D2 will remains off for interval 0 to pi, which is represented like this. So this is a working operation associated with a full wave rectifier. So means it is observed that output voltage is available for a entire one cycle, whereas for a half wave rectifier, output voltage is available only for a 0 to pi, not for a pi to 2 pi. But here output voltage is available also for a pi to 2 pi duration also there. So means it can be a called as that for a this circuit, output voltage is available for entire one cycle or entire one full wave. So it's called as a full wave rectifier. Okay, so now what will be a analysis associated with this one? So guys, remember that during the positive half cycle, only one diode is a conducting it. During the negative half cycle, lacks another diode is a conducting it. So means during the positive half cycle, half wave rectifier. Sorry, during the positive half cycle, full wave rectifier is just like a half wave rectifier. If you remove this portion during the positive half cycle, D2 is off. So D2 is internally open. So this connection is not there. So simply this circuit will be left during the positive half cycle. So can we call this one? So this circuit will look like a half wave rectifier. What about the during the interval of pi to 2 pi? During the interval of pi to pi, 2 pi, D1 is off. It's a internally open. So this track will be open. So this input is not applied here, but this input is applied. So if we take it this one connection, so this connection is connected to this one, and if you take a slightly mirror image of this one diagram, you will have just same like as a, or if you vertically take it mirror, if you vertically rotate the waveform, it's a circuit, you will have the same as a half wave circuit. So means here remember that at a time one diode is a conducting, so at a time only one forward resistance is a coming in picture. Now we want to go for the analysis associated with this one. So we will take it this analysis by considering we are familiar with half wave rectifier analysis. So we will take it analysis by considering that. So what is the first analysis? Average DC load voltage, load current, and the average DC voltage. Yes, so we want to find out. So this is associated with the load. So for the output voltage, you have the observe that output voltage is available for a, or output current is available for, here it is output voltage is available for 0 to pi duration. Yes, for half wave rectifier, one cycle is available for 0 to 2 pi. Remember guys, 0 to 2 pi for a half wave rectifier. For full wave rectifier, it's a one duration is from 0 to pi, and this cycle is repeating. Yes, so you have the interval is 0 to pi. Now we want to find out RMS. So interval is again a 0 to pi. 0 to 0 TO 2 pi. Yes. So the average load current is given as a for one cycle of output, not an input guys. So one cycle duration is a pi, and its interval is a 0 to pi, and its a function is given as in terms of a current Im sine omega t d omega t. So by using integration properties, you have to find, and this value you will have IDC is equal to 2 Im divided by pi. Similarly, we can find here that average load voltage. Here it is, what is Im? Im is given as a peak of a transformer secondary to the resistance offered by that branch or that loop. What is that loop? Loop is considered transformer secondary, diode, and the load. So transformer secondary offer its resistance, diode also offer resistance since it is in forward bias and the load is already connected. So you have this one. So similarly, we can go for the average load current. What will be average load current? Average load current can be given by considering the VDC is equal to 1 cycle by using this expression, or you can find VDC is equal to IDC into RM. So already you have found out it IDC, which is a 2Im divided by pi. If you simply plug this one, you will have this expression. Yes, we know that what is Im? Im is given as a Vm divided by Rs plus Rf plus Rs. So simply if you plug this all this, so this expression you will have alternative form. So you have the number of expression for VDC as a VDC is equal to IDC into RL. This is one. Second is the Im divided by pi into RL, and third is 2 Vm divided by R pi into Rs plus Rf plus RL into RL will be there. Now if we consider that the load resistance is large as compared with Rs plus Rf, this addition of these three terms is approximately RL. So finally this approximate RL will be cancelled with RL, and so finally we will have the VDC is 2 Vm divided by pi will be left, and so we will have the VDC is equal to approximate Vm divided by pi. IDC is Im 2 Im divided by pi. This is for full wave rectifier. What about for half wave? Im divided by pi and the Vm divided by pi. Now this expression can be slightly rearranged in terms of IDC. So here this RL is written as some additive form and some additive form and subtractive form. So here Rs plus Rf is added in this RL expression, and that is also same subtracted. So finally you will have that. Yes. So if we resolve this expression, this Rs plus Rf plus RL will be cancelled by distributing this expression, and minus of Rs plus Rf divided by Rs plus Rf plus RL will be left. So if you distribute this function, yeah, you will have 2 Vm divided by pi minus 2 Vm divided by pi into Rs plus Rf plus, Rs plus Rf divided by Rs plus Rf plus RL. Now, what is this value? Can you write this value? 2 Im divided by pi into Rs plus Rf plus RL. Yes guys, actual expression. So you will have it is a IDC is 2 Im divided by pi. This is the approximate value. Yes. So if we consider this expression, 2 Vm divided by pi into Rs plus Rf plus RL, this entire expression, yes, it can be written as a IDC. So finally you will have here VDC is equal to 2 Vm divided by pi minus IDC into Rs plus Rf plus RL. So at the end of this topic, you have the numerical to solve based on these expressions. Yes, where you need to find what is the voltage regulation, no load voltage, and the full load voltage. So these two parameters we have found already. Now next we will go for the RMS load current and RMS the load voltage and the current. So what will be RMS? It's a root mean square of a current flowing through a diode. It's given over one cycle, and one cycle is what? 0 to pi. So the entire cycle duration is a pi, and duration starts from 0 end at a pi. So if we simply plug all this, so you will have this expression. So simply use the trigonometric rule for the sine square. Since we sine square, integration of a sine square is not possible by the trigonometric property, by the integration rule. So we have to convert this sine square omega t into the another form by using a trigonometric property. So if we solve these expression, you have that finally ILRMS is equal to Im divided by root 2, whereas for half wave it is a Im divided by 2. For here it is a Im divided by root 2. Please remember that. For half wave rectifier, it's Im divided by 2. For full wave rectifier, Im divided by root 2. Why? Because here current is flowing through each half cycle. Each cycle is there. For each positive half cycle, negative half cycle will be there. Now, similarly, if we find the load resistance by using either this expression or by considering this expression, VLRMS is equal to ILRMS into RL. So you have this value which is Im divided by root 2, you will have this expression. So what is IM? Again Vm divided by Rs plus Rf plus RL. So you will have this is the alternative expression for this one. Finally, if we consider that RL is large as compared with Rs plus Rf, we will have this expression is the approximate expression will be Vm divided by root 2. Remember guys, again here for full wave rectifier, its RMS value is Vm divided by root 2. For half wave rectifier, it was Vm divided by 2. This is a significant difference in that. Now next is the ripple factor. What is the ripple factor? Ripple factor gives you how much amount of AC contents are present in the DC. And it's by definition it is given as a ripple content to the DC content. So the ripple content can be given as in terms of a voltage or in terms of a current. So therefore, ripple factor is given as ripple voltage to the DC voltage or ripple current to the DC current. Now we want to find out what will be a DC current and the DC voltage and DC current already we know in the previous analysis. Now our job is left, we want to find out either a ripple voltage or a ripple current. So we will find that for half full wave rectifiers by considering the same analysis of a half wave rectifier. So we have RMS value S is given as a RMS square is equal to IDC square plus RMS value of a ripple square, and we are interested for a ripple, so we will slightly rearrange. So you will have is equal to under root IRMS square minus IDC. So you will have this one. So to this expression, if we divide it by IDC, so you will have the ripple factor R. Yes. So what is the IDC? IDC is given as what? Sorry, or we want the IDC. So if you simply divide this IDC, and so this IDC is entering into the square root as a square term. So IDC square. So you will have this ripple factor RMS value of a ripple contained to the DC value of a ripple, DC value of the voltage current is given as a under root RMS square minus IDC divided by IDC, and if you resolve this, you will have RMS divided by IDC bracket square minus 1. And we know the we know the IDC, we know the IRMS. So what is these two values? So VDC is what? 2 Im divided by, what will be 2 Im divided by pi, and what is the RMS value? Im divided by root 2. If you simply plug these, two values, so you will have the ripple factor as a 0.482. Yes, so which is a 48.2%. What is for half wave rectifier? For half wave rectifier, this ripple factor is a 1.21. Yes, whereas for this case, for this full wave rectifier, it is a 0.48. So means here it is the same that ripple factor for full wave rectifier is a drastically improved. Yes. Now what is the voltage regulation? Voltage regulation by basic definition is given as a no load voltage minus full load voltage divided by full load voltage. Now what is no load voltage? When load is not connected. Yes, which is given as this one. Yes, and when load is connected. So the expression for this one is given as a yes. So for this circuit, yes, we will come to this again diagram. Okay. Yeah. Okay. Now during the positive half cycle, how much voltage is available at transformer secondary? Can you predict that? Transformer secondary during the positive half cycle? Just only the transformer secondary entirely. Don't don't connect this one circuit. So if you think that the peak of this one as well as the peak of this one are appeared for once half cycle. So means it will be appear as a two peaks and which is represented as a 2 Vm for a half cycle pi duration. So finally this can be a just a minute guys. Okay. Yeah. So you will have, so VDC is equal to 2 Vm divided by pi, okay, into when the load is connected. Yes, if we apply their Kirchhoff's voltage law to that diagram, yes, so you will get it this value 2 Vm divided by pi into RL divided by RS plus RF plus RL. This is a when load is connected. If load is not connected, then the transformer secondary voltage is available, which is a 2 Vm divided by. So if you simply plug all these, again you will have the voltage regulation expression is Rs plus Rf divided by RL into 100. So this voltage regulation is the same as with a half-wave rectifier. From voltage regulation point of view, there is no improvement in the full-wave rectifiers. Next, next efficiency. Now, what is the efficiency? Efficiency is given as a PDC divided by PAC. Yes. So we want to find out a PDC for full wave rectifier. PDC is given by power law. It's a PDC square into RL, and PDC is equal to IDC square into RL, and IDC already we have found. Similarly, we know that PAC can be given as a RMS square into resistance offered by that entire branch, RS plus RF plus RL. So simply if you plug all these, so you have that efficiency of a circuit is 8 divided by pi square into RL divided by RS plus RF plus RL. For half wave rectifier guys, this is slightly changed. It's here 4 divided by pi square. So finally we will have that if you consider again RL is a very greater than RS plus RF, then you will have a efficiency will be 0.812, which is improved. This means that here out of 100%, 81% is a converted in full wave rectifier, whereas halfway it's a 40% will be there, 40.7% will be there. So improved. Next is the transformer utilization factor. So what is the transformer utilization factor? It is given as a PDC divided by PAC rating. So here guys, remember that the transformer utilization factor is found by considering a transformer secondary voltage on upper half of a transformer as well as the lower half of a transformer secondary with respect to the primary winding. So means we want to find out here TUF of here we have upper half of a transformer secondary and lower half of a transformer secondary with respect to primary we need to find. So we need to find transformer secondary upper half, lower half, and we need to take average of these two. So then you will have the TUF of our transformer secondary. So it's given as a yes transformer primary to transformer secondary half of these two, averaging of these two parts. Okay. So this discussion guys. Okay. Now next time guys we will take a transformer utilization factor discussion, numerical based on that one. All these discussions we will take it next time. And I request all the guys once our meeting is over, so once our lecture is over by default by the counter time, then you have to send your attendance as a serial number, surname and the first name on our WhatsApp group. And I request all the guys here to subscribe for my channel for getting the new uploaded video lectures about the whatever the lectures are delivered. So here we have taken a working operation of a full wave rectifier. Few of the parameters we have analyzed is that IDC, VDC, ILRMS, VLRMS, yes, and we have found out the ripple factor which is a 48.48 or 48%, and also we have seen it's a voltage regulation which was the same as with the happier rectifier will be there, and rectification efficiency we have found out it. It's a major so if you observe that here for half wave full wave rectifier, DC saturation of a transformer is resolved by taking a in spite of a normal transformer, yes, CT transformer is used. So guys, I request all of you, you have to submit your attendance on a WhatsApp group. So next time we will start a discussion on a transformer utilization factor of a full wave rectifier and further discussions. So, okay, thank you.